This video is part of the chapter competition in the course Evolution of Plant Interactions at the Ostrava University. Previously, we saw how Tillman's resource ratio model explains the coexistence of multiple species competing for multiple resources. According to this model, a habitat can support as many species as it has limiting resources. But this is only possible if the species requirements are such that each is the most competitive for one resource, but not for all others, namely each species has a different competitive strategy. There are as many critically limited resources as there are species, and the resource supply point of the habitat is such that no resource is critically limited at the moment of the species establishment. This is a tall order, and such conditions are almost never observed in the nature. Quite a lot of habitats are characterized by one limiting resource and yet can support many different species. If a single resource is limiting to all plants, as seems to be the case for nitrogen in the old fields and prairies of Cedar Creek Natural History Area in Minnesota, the USA, this theory predicts that a single species should eventually dominate the entire habitat. However, despite the strong experimental evidence that nitrogen is the only limiting resource, except in a drought year when water becomes limiting, Cedar Creek fields contain from 70 to more than 200 species of vascular plants depending on the season and the year. Observations over the whole decade between the 1980s and 1990s show that these species are persisting in the fields, and the species that were driven to low density because of the drought are reinvading and becoming re-established when water levels increase. All of this suggests that 70 to 200 species are stably coexisting in a habitat in which the only one demonstrably limiting resource is nitrogen. So what does this mean about the resource ratio model? Should it be just ignored because it's incorrect? But remember, all models are false, and some are useful. Tillman's model is very useful to explain the competition of a limited number of species in a precise experimental design. But the model is implicitly based on 4 very strong assumptions, which are not realistic in a natural habitat scenario. First, that all organisms within a habitat experience exactly the same resource concentration at the same time. Next, organisms live in a spatially homogeneous habitat. Next, all interactions go to equilibrium eventually. And finally, the entire food web can be approximated by just the link between consumer species and their resources, ignoring all other interactions. Each of these assumptions can be relaxed while holding the other 3 true. This produces a slightly more complex model that can account for the maintenance of multiple species with a restricted number of limiting resources. So first, let's see how the model's prediction will change if we assume that not all individuals have the same access to resources at all times. The models of resource competition presented above assume that all individuals of all species experienced exactly the same resource concentration at any given instant. As the number of individuals in a habitat grows, the resource availability decreases equally for everyone. This is obviously an unrealistic assumption, as plants rarely have an effect on resources that are situated far away from them. Instead, a more realistic assumption would be that individuals occur at spatially discrete patches of resources, and they only affect the resource dynamic locally on their own patch without affecting the neighboring patches. This is what we call a metapopulation model. The assumptions of this model are: the habitat is a series of patches, each of which can be approximated to a subpopulation in a metapopulation. Each patch supports exactly one individual. The species are ranked by their competitive ability. This can be approximated to Tillman's R-star, with the most competitive species having the lowest R-star because they can deplete most of the resources of the habitat and still survive in it. All of these assumptions make it easy to calculate the species abundance, which is simply the proportion of occupied patches. Can you calculate the species abundance in this theoretical example? The total number of patches is 16. 8 of these patches are occupied by the same species. The percentage of occupied patches is 8 out of 16. That gives us a species abundance of 0.5 or 50%. We note species abundance as small p. Obviously, we can just as easily calculate the proportion of non-occupied patches, which is the inverse of p, or 1 minus p. In this case, 50% of the patches are non-occupied. Next, the model assumes that for a given species, dispersal is possible and equally probable to all patches in the population. So the seeds are equally probable to be dispersed to a neighboring patch as they are to be dispersed to a distant patch. This is quite an unrealistic assumption, but it really simplifies the model's estimates. If a seed falls in a patch that is empty, the species will be able to colonize the patch. If the seed is dispersed in a habitat that is already occupied, there are two possibilities. The resident species is just as good or even better competitor, so the patch won't be invaded. Or the resident species is a weaker competitor, so the patch will be invaded by the better competitor. The colonization ability is different for different competitors. Some can colonize many patches because they produce many seeds. Others can colonize only a few patches because they produce only a few seeds. And lastly, an individual can also disappear from a patch without competition because it dies out. In this case, the dead individual will liberate the patch that can be freely colonized by other species. Now that we have described our model, let's see under what conditions can two or more species coexist. A given species abundance will increase with its colonizing ability and will decrease as plants are lost. This includes plant mortality without competition and competitive displacement by species which are better competitors. Two or more species can coexist if there is a trade-off between their colonization and their competitive ability. Specifically, species which are good competitors should be poor colonizers, whereas poor competitors should be good colonizers. Coexistence occurs because the superior competitor is unavailable to occupy all sites within a given habitat. Even in the absence of other competitors, there is a portion of the habitat that is always unoccupied by the best competitor because the competitor has low colonization ability, so quite a lot of patches remain unoccupied because it simply cannot produce enough seeds to colonize them. The species colonization and loss rate are such that there is always a proportion of patches that are left unoccupied. These empty patches can be occupied by an inferior competitor, which is a better colonizer. The colonizer is regularly being displaced from the patches it occupies by the superior competitor. However, as there are enough empty patches, the colonizer can persist in the metapopulation by colonizing these patches. The colonizer will be regularly displaced by the competitor, but because the competitor cannot occupy as many patches as the colonizer, there will always be a possibility for the colonizer to invade new empty patches. As long as there are empty patches in the population, a third species can arrive, that is even a better colonizer and worse competitor than the other two. This dynamic can go on for a large number of species, resulting in a metapopulation where all species can be ranked by their competition and colonization ability, which are negatively correlated. So there you have it, the metapopulation model. Based on all of these assumptions, this model supports the coexistence of an infinite number of species as long as there is a competition-colonization trade-off that can perfectly rank the species by their abilities, and available empty patches that sustain individual growth.